Yay!
Yay! All right, we'll start off with a quick example of vector products by evaluating the dot product or scalar product first. We'll just do a quick example. We'll do a lot of these as we go along. Vector products and dot products in particular are really, really important, but we'll just do a quick example to show what it is we're doing. Here we have, let's suppose, a cube, and the cube is 1 unit. Let's just keep it really simple, 1 unit on a side. And we can use the dot product to find out the angle between any two vectors, which is kind of neat. It's not obvious here in this case. What's the angle between those two vectors? That's not an obvious thing. You might think, oh, it's a cube. It should be 45 degrees. It's not, because you kind of know. I mean, imagine that vector A kind of through the long diagonal of the cube. That vector A is longer than the vector B. B only has to go through a square. A is a longer vector. So that can't be a 45-degree angle, right? It's got to be less than that. So let's figure out what that angle is. And the way we're going to do it is with the dot product. Here's the general idea with the dot product. If I have a vector A and a vector B, what does it mean to multiply two arrows together? They're just arrows, right? Well, I don't know. I don't know what it means, but we can define what it means in a way that's useful. And one thing that's useful, one thing we do know how to do is multiply numbers together. So in what sense are A and B like numbers? They're lengths. Their lengths are like numbers. So what if I asked, how much of A is going in B's direction? Could I sort of project A onto B, or maybe find the shadow, right? What's A's shadow on B? So how much of A is going in B's direction? It would be this much. And then what I could do is I could multiply those two lengths together, right? Because they're both going the same direction. And that would give me that would give me a number. And it turns out that in physics, that number is useful. So if there's an angle theta between these vectors, what is the amount of A that's going in B's direction? Well, if you just use your trig, A cosine theta is the amount of A that's going in B's direction. So when we multiply them together, we just get this thing that we're going to define as, those three little equal signs means defined as, we just define this thing to be the dot product, or what's called the scalar product, because we just get a number. It's just A, B, cosine theta, right? That's just the amount of A that's going in B's direction times the length of B. And notice that's just a number. That's why it's called the scalar product. It's not a vector. It's just a number. And it's just a definition. And then also, you might have been taught this. If you have an AX, AY, AZ. Remember, I like to write my vectors in column notation, BX, BY, BZ. The thing below left, AB cosine theta, in some class or other, we're not going to do it here, in some class or other, you proved that this is exactly the same as if you do this. You just multiply the components and add them, AY, BY, plus AZ, BZ. Right? Those two things, it turns out, multiplying the components together and adding them, and then AB cosine theta, those are exactly equal to each other. It's just two different ways of doing it. So here's what we're going to do. How does this relate to the cube? What we're going to do is we're going to find that theta by doing this. So this implies that cosine of theta is just going to be the dot product divided by the product of the lengths. Neat. And then we'll just do the inverse cosine to get the angle at the end. All right, so our task is we need to find what the dot product of these two vectors are. How we're going to do that is first we need to write down what the vectors are. Okay, here we go. What is the A vector? Okay, here's what I'm after. How do we get from the beginning to the end? Right? Remember, all the sides of the cube are 1. So how am I going to get from the beginning of A to the end of A? Well, it looks like what I'm going to have to do is I have to go 1 in the x direction. Just pick out its components. I go 1 in the x. What do I have to do in y? I have to go -1 in the y. And then I got to go up 1 in the z to get there, right? That's the recipe to get there. And that's the vector A. The vector B, from the beginning of B to the end of B, what I'm going to get is I have to go +1 in the x, and I'm going to have to go -1 in the y. And I don't do anything in the z, right? I stay in the xy plane, so it's going to be 0. So there we go. Those are my A and B vectors. So next, I need to take their dot product. Well, I'm just going to follow I know the components, so I'm going to follow the recipe that we already wrote down. So A dot B is going to be, okay, I just do what it says. AX BX, 1 times 1, 1. Plus AY BY, -1 times -1, 1. And then 1 times 0, 0. Right? And then I just add them together. So the dot product is just a number, and it's 2. So the dot product of A and B is 2. So now I'm almost home, right? So cosine of theta is just going to be A dot B. Well, we already found that. That's 2 divided by AB. Okay, now I just need the lengths of those vectors. Well, that's pretty easy because the length is just the square root of x squared plus y squared plus z squared. Look at A. The square root of, well, x squared plus y squared plus z, so that's going to be the square root of 3. And what's the length of B? Looks like the square root of 2. So this is just going to be 2 over the square root of 6. And when I do this, I get 0.816, right? So what I get at the end, when I take the inverse cosine of that, the inverse cosine of 0.816, by the way, make sure you're in degrees if you're following along at home, right? If you're in radians, this is bad news. So in degrees, I'm going to get, what did I get? 35.3. Neat. So that's the angle between A and B. So this is something we'll be doing over and over and over again, finding vectors, finding the angle between vectors, finding the dot products between vectors. So this is kind of a simple example with simple components, but it really doesn't even matter, right? If A and B had any components at all, the recipe is pretty easy. You just multiply them together and add them like numbers. It's just arithmetic. All right, next up is going to be cross products.